This question is from May-June 2017, paper 12, question 5. It's about to calculate the resistivity of a block of a semiconductor when a current of 30 milliamps is flowing through, and it provides the voltage across the block. And this question also provides the uncertainty of the voltmeter as 0.1 volts, the uncertainty of the ammeter, which is 0.1 milliamps, and the uncertainty of the length, which is 0.2 millimeter. After all that, is asking what is the resistivity of this block semiconductor. And here are the options. So I'm going to explain step by step how to solve this question. So the first step is to find the formula with resistivity. And here we go. We have this formula right here that is related to the resistance of a wire. So this rho represents resistivity, L is the length of the wire, and A is the cross-sectional area. So now we are going to rearrange this formula in terms of resistivity. So this is the formula that we are going to be working with. Now, unfortunately, we don't have the value of the resistance of this block semiconductor. Was provided the current that flows through the conductor and the voltage across the conductor. So we need to use those values to calculate the resistance of the conductor using the current and voltage provided in the question. So those are the values that were provided. Current is 30 milliamps and voltage is 10 volts. Now remember, we do not use uncertainties of the current and voltage to calculate the value of the resistance, just the main values. Now, from the Ohm's law triangle formula, we can find a formula here for the resistance of the wire in terms of its voltage and current. So now, after doing value substitutions, we have that the resistance is 333.33 ohms. I don't like to round when we are in the middle of a calculation. I usually round at the end. So let's keep the number as it is. Okay, so in our first step, we calculate the value of the resistance in terms of the voltage and current that were provided in the question. So now that we look at this formula, it's still missing the value of the cross-sectional area and what are you going to do for length. Okay, so let's look in details here. The cross-sectional area is the shaded gray part of this block, and we can calculate as follows. So the area is the width times length. Now remember that we are doing operation with prefixes. This first M, millimeter, milli, the multiplier is 10 to the minus 3. So remember that you have to add those exponents. Here we have for this M minus 3, and for the next M we have also minus 3. So we add them and we get minus 6 as the final value of the exponent. Now a question students usually ask, so why this area, the shaded gray, and not this one? So remember, this area here is the cross-sectional area. Cross means that it's kind of perpendicular to the direction of the current. So the current is coming this way, so it's going to cross this area, not the top one, right? So that's how we do. And the length, of course, is the length goes with the direction of the current. So the length here is 15. So this is the length and this is the width. All right, so the length is 15 m. Remember this m here is the prefix 10 to the minus 3. And now we are doing value substitution in this formula. We have all the elements. We have the resistance, we have the area, and we have the length. So there we go. We have the resistance that we calculate on step 1, and this is the area, and this is the length. So we combine all these. Please try in your calculator, because sometimes with all this work and we have a minor error at the end to do kind calculations. So you should have the value of the resistivity 10 ohms meter, and that's the unit for resistivity. Third step, we are going to calculate the uncertainty of the resistivity, because the options of these questions are showing all the value plus minus its uncertainty. So we need to calculate that. So how we do this? So first you need to look at the original formula. So that's the formula for resistivity. Now to calculate the uncertainty, we are going to add the uncertainty of every single variable that you see in the formula. You are going to add the uncertainty of the resistance, the uncertainty of the area, and the uncertainty of the length. So let's look at how we are going to do this. Number 1, let's work by steps. So here, the uncertainty of the resistance, we need to take in consideration the formula we used to calculate the resistance. So we need the value of the current now with its uncertainty that was provided in the question, and the value of the voltage with its uncertainty. So here I state what was provided in the question. So the electrical meter used are accurate to plus minus 0.1 milliamps. So that's how you represent the value of the current plus minus its uncertainty. Now we need like a formula, if you have one, when you need to calculate uncertainties. So we are going to start with resistance. So resistance is voltage over current. Now that we have the values for the voltage and for the current with their uncertainties, we can go ahead and calculate the uncertainty of the resistance. So here is how we do. It's a term that is called fractional uncertainty, because at the end we do have a fraction here. So that's how it works in simple ways. So we get the value of the uncertainty divided by the value of the variable. So in this case, for voltage, 0.1 divided by 10, and for current, 0.1 divided by 30. Now notice here, because both have the same units, I don't use the multiplier for the prefix, because it's going to cancel anyway. So you don't have to do that, just get the uncertainty divided by the value. So when you add those, you are going to get a very small number, of course, 0.01333, no units, because here we cancel the units when we do the fraction, voltage, milliamps and milliamps. So the result of the uncertainty, no units. Now let's work for area. So area is width times length. So here we have the width 30 plus minus 0.2 mm. So this uncertainty was provided in the question. And the length, likewise, 15 plus minus 0.2 mm. So we do the same that we did for the resistance. We are going to add the fractional uncertainties from each variable that we see in the formula here. So how it goes? So here you have 0.2 divided by 30 and 0.2 divided by 15. Adding both, you have 0.02. Now, because length, there is no formula, but I know the uncertainty is 0.2, the same one that you measure here for area. So to calculate the uncertainty of length is straightforward. Is 0.2 divided by 15, which is, by coincidence, the same number that you have for resistance. So now we are going to add all partial uncertainties because those partial uncertainties cause error in the value of resistivity because it's here, right, in the formula. So don't worry about this. All that we need to do is add those partial uncertainties for each item in the formula. Pretty much that's what we are doing here. So we are going to add all three, and we have this value right here. Again, no units. Now, because the uncertainty of the resistivity does not have units, we need to add a unit. How we do that? By multiplying by the value of the resistivity that we calculated before. And so this times this uncertainty is 0.47 ohms meter. So usually for uncertainty is a good practice, use just one significant figure. So we are going to round to 0.5 ohms meter. Now back to our original question. Let me look the option that matches with my result. So is option C. Alright guys, this is the end of this video and I hope you learned something, and thank you for watching.